In this lecture, we're going to be looking at the binomial theorem, which will give us an efficient way to raise a binomial to a positive integer power. Before we can get to the binomial theorem, we have to learn a little bit of notation. The first bit is factorial notation. If n is a positive integer, then n factorial, which we denote by n followed by an exclamation point, is the product of n times the integer below that, which is n minus 1, times the integer below that, which is n minus 2, and we keep reducing the factors by 1 until we get all the way down to 1. Multiply all those factors together. In other words, n factorial is the product of all positive integers less than or equal to n. Now you'll notice this rule only applies to positive integers, so we have a special rule for 0 factorial. 0 factorial is defined to be equal to 1. We don't follow the rule above because 0 is not a positive integer. This gets its own rule. So just a few examples. This first thing you see here isn't 3. That's not excitement about the number 3. That's 3 factorial, and it's defined to be the product of all positive integers less than or equal to 3. So it's 3 times 2 times 1, which is 6. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. 5 times 4 is 20. 20 times 6 is 120. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And that comes out to 40,320. Now you might wonder why we have a 1 in the definition, because multiplying by 1 doesn't contribute anything. We need it for this last one. 1 factorial is just 1. Start at 1, end at 1. Now factorials pop up in lots of different places in math. In particular, you see them a lot when you're trying to count the number of ways that something can happen. For instance, a factorial on its own will tell you the number of ways that you can arrange that many objects. So the number of ways you can put 3 objects in an order is 6. If I take the letters A, B, C and find all of the possible arrangements of those letters, you can see there are 6 different ways you can arrange those. So factorials get used a lot for what we call counting problems. And we need to do a special kind of counting where we're selecting k objects from a set of n objects. You'll see why when we get to the examples. But we need that formula, and it depends on factorials. The number of ways to choose k objects from a collection of n objects is n factorial divided by k factorial times n minus k factorial. This formula will count how many ways you can select k objects from a collection of n objects. There are a few different notations for this. My personal preference is the notation where you stack the two numbers inside tall, skinny parentheses. We read this n choose k, which is nice because it tells you what it does. It counts the number of ways that you can choose k objects from a set of n objects. Another notation you'll want to be familiar with because the calculator uses it is nck, where the n and the k are subscripts. There are other notations for this as well. I'm not going to introduce those because we're not going to see them. Let's look at an example where we use this formula, and we'll make it simple enough that we'll be able to check the answer by listing out all of the possibilities. 5 teams participate in a round-robin tournament. A round-robin tournament is a tournament where each team plays against each other team exactly once. How many games will be played in the tournament? Well, if there are 5 teams and we need to choose 2 of them to play each other, how many different ways can we do that? Well, that would be 5 choose 2. And our formula says that 5 choose 2 will be 5 factorial over 2 factorial times 5 minus 2 factorial. 5 factorial over 2 factorial times 5 minus 2 factorial. That's 5 factorial over 2 factorial times 3 factorial. Now 5 factorial and 3 factorial we already calculated. 5 factorial was 120, 3 factorial was 6. So 120 here, 6 here. See if you can calculate 2 factorial. 2 factorial would just be 2 times 1, that's 2. So this is 120 divided by 12, which is 10. So according to this formula, there should be 10 total games in the tournament. Let me verify that for you. Suppose I call the teams A, B, C, D, and E. Let's start by listing all of the games that A will play in. So A will play B, A will play C, A will play D, and A will play E. Now let's list all of the games that B has remaining. We already have B versus A. So we also need B versus C, B versus D, and B versus E. Now we'll list all of the remaining games for Team C. They still have to play Team D and Team E. And then Teams D and E still have to play. How many games is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I know that doesn't prove that this formula always works, but I hope you believe me that it works every time. This is a simple example that shows that. Now in this example, it wasn't too difficult to do this by hand, but I want to show you how to do this with the calculator. Start by typing in the value of n, which is the bigger number, so type the 5. Then I want you to push your math key, which is directly underneath your green alpha key. And I mentioned that these factorials are often used for counting problems. Counting is often done in probability problems, so you want to scroll to this probability heading. And the option we want uses a different notation than we're using. The calculator calls this NCR, N choose R. So you want to select that third option, then put in the smaller number, which in our case was 2, and we get that 5 choose 2 is 10. We won't be calculating N choose K by hand very often. We're either going to use the calculator or another shortcut instead of doing them by hand. Let's do another example that's way nerdier but closer to what we want to be able to do. In the expression x plus y times x plus y times x plus y times x plus y, how many ways can you circle exactly 2 of the y terms? In other words, how many different ways can we choose 2 of the 4 y's? If we need to choose 2 out of 4 objects, that should be 4 choose 2. Now 4 choose 2 is easy to do by hand. It's 4 factorial over 2 factorial, 2 factorial. And if you want to practice it by hand, go ahead. I want to review how to do this with the calculator. Start by typing the larger number, which is the 4. Math key. Scroll to the probability heading. You want choice 3 and choose R. Type the smaller number, hit enter, and we get 6. So there should be 6 different ways that you can circle 2 of the 4 y terms. Let me verify that for you. We could circle the first and the second. We could circle the first and the third. We could circle the first and the fourth. Or we could do the second and the third. We could do the second and the fourth. Or we could do the third and the fourth, the last 2. Those are all of the different ways. You can see there are 6 ways we could have done that. It was much faster to use the calculator function than it was to list them all out, and that was for a small example. Now this leads into the binomial theorem because what we're going to learn to do is come up with the expansion of this product without following the arduous distributive property on every single factor. Instead, we're just going to take advantage of the fact that we're just choosing some of these terms for our product. Here's what the formula says. Let n be a positive integer. Then when you raise a plus b to the n power, so you're raising a binomial to a positive integer power, you get the following expansion. The first term of the expansion is just the first term of the binomial raised to the nth power. That's just multiplying all of the first terms together. In the second term, you want to think of it like you're choosing 1b. So you're choosing 1 less a, and therefore you're choosing 1b. There's a b to the first. How many different ways could we choose 1b from the n factors? Well, n choose 1. In the next term, we're going to select 2 b's, which means we're only going to select n minus 2 a's. We continue that pattern until we get all the way down to choosing all b's. There's only one way to do that, and that's to choose a b from every single factor. This is the binomial theorem. There is a much more concise way to write this using summation notation. We're finding the sum from k equals 0 to n of n choose k, a to the n minus k, b to the k. So for example, in this third term, that would be n choose 2, a to the n minus 2, b squared. This formula is nice for brevity. This one is a little bit more explanatory. You can remember it however you want. Let's put it into action by looking at that example. Let's expand x plus y to the 4th power using the binomial theorem. Let me write the rule on this slide. So here's our version of the binomial theorem. what I want to do is raise x plus y to the fourth power. So the first term of the expansion is the first term of the binomial raised to the entire power. So that would be x to the fourth. The next term will be 4 choose 1 times x to the, well, we're going to reduce the power by 1. We're only choosing 3 x's, and we're going to choose 1 y. The next term calls back to what we did in that nerdy example. We want to choose 2 of the y's. How many different ways can we choose 2 of the y's? Well, we said that was 4 choose 2, 6. We're choosing 2 y's, and so therefore we're choosing 2 x's. Notice that the power on x went down by 1, the power on y went up by 1. This happens every single time. Next time we're going to choose 3 y's. Well, there's 4 choose 3 ways to do that. We're choosing 1 fewer x because we're choosing 1 extra y. And now we're going to run out of x's. So that means all we have are y's, so there will be 4 y's. The coefficient here will be 1 because there's only one way to do that. Now we just have to calculate these binomial coefficients. We already calculated this one to be 6. But we need 4 choose 1 and 4 choose 3. I'm going to use the calculator for 4 choose 1, but when you see the answer it should be obvious. If I type 4, math, scroll to probability, choice 3, 1, we get 4. Why do I think that should be obvious? This is asking how many different ways can we choose one of the 4 y's. Well, there are 4 different ways to choose one of the 4 y's because there are 4 y's total. I claim this last one is also obvious because if we're choosing 3 y's, well then we're only choosing 1 x. So how many different ways can we choose 1 x? Well, I claim it's 4. Let's show that with the calculator. 4, math, scroll to probability, choice 3, and this time we're choosing 3 y's. But that's equivalent to choosing 1 x, so there's only 4 ways to do that as well. And we get this expansion, x to the fourth plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the fourth. I claim that's the correct expansion, and to prove that to you, I've done it the long way. So here I took x plus y to the fourth, I wrote it out as 4 copies of x plus y, I used the FOIL process on the first 2 and the last 2 to get x squared plus 2xy plus y squared, and then I used the distributive property to get all 9 possible products there, and I collected the like terms, I underlined the like terms in the same color, and I got x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. Same answer. Notice that it's significantly less writing and significantly less work to use the binomial theorem. I know it's not hard to do it this way for x plus y to the fourth, but if we had a much larger power, it would be very, very arduous to multiply it out the long way. The binomial theorem won't take very long at all, especially if we're using the calculator or some other trick to get the binomial coefficients. The other trick to get these coefficients is to use what's called Pascal's triangle. Let me explain how you create it, and then I'll show you where those coefficients come from. You start by writing a triangle of 1's at the top. So a 1 in the very first row, and then 2 1's in the next row. For every row after that, we're going to continue writing 1's on the edges, but we're going to generate the central terms by adding the terms directly above it. So to get this 2, we add the 1 plus the 1. 1 plus 1 is 2. To get to the next row, 1's on the edges, and then this entry is 3, and this entry is 3 because 1 plus 2 is 3, and 2 plus 1 is 3. To get the next row, 1's on the edges, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, 1 on the edge. Let me stop here because you might recognize these coefficients. 1, 4, 6, 4, 1 is exactly the list of coefficients we have in our expansion here. So this is 4 choose 0, this is 4 choose 1, this is 4 choose 2, which we've already verified a couple of times. This is 4 choose 3, this is 4 choose 4. So Pascal's triangle generates the values of n choose k. You just have to make sure you go to the correct row. Let's generate just to make sure you understand it. We put a 1 on the edge. 1 plus 6 is 7. 6 plus 15 is 21. 15 plus 20 is 35. 20 plus 15 is 35. 15 plus 6 is 21. 6 plus 1 is 7, and then a 1 on the edge. So this is 7 choose 0, this is 7 choose 1, this is 7 choose 2, this is 7 choose 3. Let me stop here and prove that to you. I'm going to show you this is 7 choose 3 using the calculator. 7, math, scroll to probability, choose 3. 35, just like we got. So now you have two ways that you can generate these coefficients. You can either do n choose r in your calculator, or you can just go to the appropriate row of Pascal's triangle. And you don't need to memorize the triangle because you can just recreate it. The only time it might be an issue is if you have to go to like the 10th row. It might be more efficient to go to the calculator. Now that we're armed with two ways to get these binomial coefficients, let's do some more expansions. This says expand the binomial 2x plus y squared raised to the 5th power using the binomial theorem. Let me copy the theorem down again. Okay, we want to do 2x plus y squared raised to the 5th. The first term of our expansion is the first term of the binomial raised to the total power. So this is 2x raised to the 5th power. In the next term, we want to choose one copy of y squared. There are 5 choose 1 ways to do that because there are going to be 5 total factors and we're only choosing one copy of y squared. If we choose one copy of y squared, how many copies of 2x are we choosing? We're choosing 4, and you can see that's exactly what you get if you did 5 minus 1. In the next term, we're going to choose one fewer factor of 2x and one more factor of y squared. So we're going to choose 2 y squareds. This is 5 choose 2. We've only got 3 copies of 2x. We've got 2 copies of y squared. Then it's 5 choose 3, because we're choosing 3 copies of y squared. If we choose 3 copies of y squared, we're choosing 2 copies of 2x. Then 5 choose 4 times 2x times y squared to the 4th. And then a y squared to the 5th. Sorry, I kind of jammed that in there. Now we need to simplify this. When you raise 2x to the 5th, you're raising 2 to the 5th and x to the 5th. 2 to the 5th is 32 times x to the 5th. We need to calculate 5 choose 1. This one I claim you should know. How many different ways can you choose one object from a set of 5 objects? Well, it should be 5. When you raise 2x to the 4th power, that's 16x to the 4th, and there's one copy of y squared. Now we need 5 choose 2, which we actually calculated when we did the tournament example. 5 choose 2 was 10. We have to cube 2x. 2 cubed is 8 times x cubed. And now we need to square y squared. When you raise a power to a power, you multiply the powers. That's y to the 4th. Now we need 5 choose 3, which we haven't calculated yet. We can get that with the calculator. 5, math, probability heading, choose 3. That's also 10. Alternatively, we could just go to the appropriate row of Pascal's triangle. How do you know which row to choose? Well, look for the row whose second entry is the value of n. So the value of n is 5, so we want this row right here. So the first coefficient should have been 1. The second coefficient should have been 5. We've got that. The third coefficient was 10. We got that. We already knew that one. And here's the 5 choose 3 that we just calculated, also 10. So we can either go to the calculator or we can go back to the triangle. We need to finish this term off. Squaring 2x gives us 4x squared. Cubing y squared is y to the 6th. 5 choose 4. 5 choose 4 should be 5. Look at the triangle. There it is. 5 times 2x times y to the 8th. And then the last term is y squared to the 5th, which is y to the 10th. The coefficient here is 1. Check the triangle. Yeah, the coefficient is 1. Now we just need to simplify this multiplication. This is 32x to the 5th plus 5 times 16 is 80, so 80x to the 4th y squared plus 10 times 8 is 80, 80x cubed y to the 4th plus 10 times 4 is 40, 40x squared y to the 6th. 5 times 2 is 10, 10x y to the 8th plus y to the 10th. And now we have the expansion of that binomial. I know it probably seems complicated because we've only seen a couple of examples, but I'm telling you it's way faster than doing this by expanding it by hand. Doing 2x plus y squared to the 5th power by writing out 5 copies of 2x plus y squared and then using FOIL and the distributive property everywhere will take much longer than using this method. You just have to get used to following this formula. Let me point some things out as we go. I want you to notice that the power on the first term is decreasing by 1 every single time. Every time. All the way down to 0 copies in the very last term. Meanwhile, the powers on the second term are increasing by 1. We had none of them here, then we had 1 copy, then 2 copies, then 3 copies, and so on. The power is the top number in the n choose k every single time because that is n. The bottom number is the number of copies of the second factor that you're choosing. So here we were only choosing 1, so you don't see it here. Here we were choosing 2, here we were choosing 3, and so on. If you think of it that way, it's not that hard to follow the formula. Then you just have to find these coefficients, and you can get those in 2 different ways. You can either go to the calculator, or you can go to Pascal's triangle and just find the appropriate row. Let's try an example with a minus sign in it. Let's expand x minus y to the 6th power using the binomial theorem. We're going to do this one without writing the formula out. This time we're going to see if we can follow that pattern. So we've got x minus y to the 6th. The first term is x. You want to think of the second term as minus y or negative y. So in the first term of the expansion, you take the first term of the binomial and you raise it to the full power. In the next term, we're only going to choose 5 x's. We decrease the power on x by 1. We're going to choose our first copy of negative y. How many different ways can we choose 1 copy of negative y from the 6 possible factors? Well, 6 choose 1. In the next term, we're going to have another coefficient like that. We're going to have 1 fewer copy of x. We're going to have 1 more copy of minus y. And we ask how many different ways can we choose 2 copies of minus y? Well, 6 choose 2. In the next term, we're going to choose 1 fewer copy of x. We're going to choose 1 more copy of minus y. How many different ways could we choose 3 minus y's? Well, 6 choose 3. Again, 1 fewer copy of x, 1 more copy of minus y. 6 choose 4 ways to choose 4 copies of minus y. 6 choose 5 ways to choose 5 copies of minus y. Notice that means we're only choosing 1 copy of x. And now we're to the very last term where all we're choosing are minus y's. We're going to choose 6 of them. There's only one way to do that. There's nothing to do in the first term. We need 6 choose 1. There's 6 ways to do that. Now we need 6 choose 2, which we haven't done before. One way to do that is to type 6 math, scroll to the probability heading, choice 3, 2, and hit enter, and we get 15. Another way to do that is to access Pascal's triangle and go to this row where the second entry is 6, and we see that 6 choose 2 would be 15. I'm going to steal the rest of my coefficients from Pascal's triangle. Let me finish off this term first. This is x to the 4th, and the negation of y squared would be y squared. Negative times a negative is a positive. Now I need 6 choose 3. Go to the triangle. 6 choose 3 is 20, the next entry in the list. X cubed. A negative times a negative times a negative would still be negative, so this is minus y cubed. 6 choose 4 is 15, the next entry in that row. X squared. 4 copies of a negative would be positive, so this is positive y to the 4th. 6 choose 5 will just be 6. You can see that's this entry right here. 6x. 5 copies of a negative would still be negative, so this is negative y to the 5th. And then 6 copies of a negative would be positive, this is y to the 6th. Simplifying those negatives, we get x to the 6th minus 6x to the 5th y plus 15x to the 4th y squared minus 20x cubed y cubed plus 15x squared y to the 4th minus 6x y to the 5th plus y to the 6th. And now we have that expansion. I used Pascal's triangle to come up with these coefficients. We could have instead gone to the calculator for each and every one. I've got one I'd like you to try. I made the power smaller here so that you won't have as much work, but I also changed it so that the second term is a number and not a variable. Don't let that change the way you do it. I want you to expand x plus 7 cubed using the binomial theorem. Okay, x plus 7 cubed. That'll be x cubed. Always start by raising the first term to the total power. Then we're going to do 3 choose 1 because we're going to choose 1 copy of 7. If we choose 1 copy of 7, then we're choosing 2 copies of x. So that's x squared times 7. Plus 3 choose 2. We choose 1 fewer x. We choose 1 more copy of 7. And now we're to the end where we're doing 7 cubed. This is x cubed plus 3 choose 1 is 3 times x squared times 7 plus 3 choose 2 is also 3. You can get that from the triangle. 3 choose 2 would be right here in this 4th row. Or we could do 3 choose 2 in the calculator. 3, math, probability, 3, 2. And it gives us 3. As an aside, another way to see that 3 choose 2 is going to be 3 is that you're only choosing one of the 3 x's. So it's got to be 3. Times x times 7 squared is 49. And then 7 cubed is 343. So simplifying, we get x cubed plus 21x squared plus 147x plus 343. This one's small enough that multiplying it out by hand wouldn't be that hard, so if you want to check this one later, you can. For our last few examples, we're not going to find an entire expansion, we're just going to find a term or two. Find the first 2 terms of the expansion of x to the 4th minus 8y cubed all raised to the 10th power. See if you can do this. The first term of the expansion is the first term of the binomial raised to the full power. The second term of the expansion is going to choose 1 copy of minus 8y cubed out of the 10 possibilities. So that's 10 choose 1 times x to the 4th raised to the 9th power. We're only choosing 9 copies of x to the 4th because we're going to introduce our first copy of negative 8y cubed. Now there are a bunch more terms, but we weren't asked to find them. We're just going to simplify these. So x to the 4th to the 10th would be x to the 40th. 10 choose 1 isn't in our triangle, but you don't need the triangle for 10 choose 1. 10 choose 1 would just be 10. If you're choosing one object out of 10 options, there are 10 ways to do that. X to the 4th to the 9th would be x to the 36th. And then this is still negative 8y cubed, plus a bunch of other terms. So this is x to the 4th minus 80x to the 36th y cubed. And then a bunch of other terms, but we weren't asked to find those. Okay, let's hop a little deeper into the list. Here we're asked to find the 5th term of the expansion of 5x plus 2y to the 6th. Now there's a shortcut to figuring out which one is the 5th term, but since this is our first example like this, I'm going to list them all out. So the first term would be 5x raised to the full 6th power. Then we're going to do 6 choose 1, we're going to reduce the power on 5x by 1, and we're going to introduce our first copy of 2y. The third term would be 6 choose 2, 5x raised to the 4th power, 2y squared. The fourth term would be 6 choose 3, 5x cubed, 2y cubed. And our 5th term will be 6 choose 4, 5x squared, 2y all raised to the 4th. Okay, so there are a few more terms, but we've arrived at the 5th term. That's the one we want. So the 5th term is going to be 6 choose 4, 5x squared times 2y to the 4th. Let's simplify this, and then we'll talk a little bit about how we could have figured out what the 5th term was without listing all of these. So 6 choose 4. I can do that with the calculator. 6 math, scroll to probability, choice 3, 4, enter. 6 choose 4 is 15. We've actually already calculated this once. We also could have gone back to the triangle. We want 6 choose 4. Be careful, this is not 6 choose 1. 6 choose 1 is right here. So 6 choose 1, 6 choose 2, 6 choose 3, 6 choose 4 is 15. 5x squared is 25x squared. And 2y all raised to the 4th. 2 to the 4th is 16, so this is 16y to the 4th. 25 times 16 is 400. 400 times 15 is 6,000, so it's 6,000 x squared y to the 4th. That would be the 5th term of this expansion. Now, I mentioned there was a shortcut. We didn't have to list all of these out. How could I figure out what the 5th term is going to look like without listing all of the possibilities that come before it? Well, notice that in the expansion after the first term, the binomial coefficient always lags 1 behind the term you're on.
So in the second term, the bottom number is 1. In the third term, the bottom number is 2. In the fourth term, the bottom number is 3. And in the fifth term, which is the one we want, the bottom number is 4. So we know the binomial coefficient of the fifth term is going to be 6 choose 4. That 4 tells us how many copies of the second term we're choosing. So that's got to be a 2y to the fourth. And if we're choosing 4 copies of 2y, then the remaining 2 terms have to be 5x. So we can put all of this together to jump straight to the term that we want. Let me show you an example of that. Let's find the 7th term of the expansion of 4x minus y to the 9th. If I want to jump straight to the 7th term, I just have to remember that the binomial coefficient is lagging 1 behind. So this is going to be 9 choose 6, not 9 choose 7. I'm choosing 6 copies of the back term. So it's negative y to the 6th. And now I have my 7th term. Now we need 9 choose 6. Since I only need this one coefficient, I'd probably just do this in the calculator. 9 math probability heading choose 6 is 84. When you cube 4x, you get 64x cubed. When you raise negative y to the 6th, you get 6 copies of this negative factor. Those would cancel, so we get a positive y to the 6th. And I don't know 84 times 64. 5,376. X cubed, y to the 6th. Let's try a slightly different type of problem that uses the same kind of logic. Let's find the term of the expansion of x cubed plus 2y to the 9th that contains x to the 12th. So we want to find the term that when we simplify it will have an x to the 12th in it. So how are we going to do this? Let's take advantage of the formula here. We know that the terms are generated by doing 9 choose something, and then we're going to raise x cubed to some power, and we're going to raise 2y to some power. We want the term of the expansion that contains an x to the 12th. So the power on here has to give us a 12. Well, remember that we're raising a power to a power here, so we'd be multiplying. So what times 3 is going to give us the 12? Well, 4. So that exponent is 4. That immediately gives away what this exponent has to be, because we're choosing a total of 9 terms. So if we chose 4 copies of x cubed, we have to choose 5 copies of 2y, because there's a total of 9 options. And since this number is a 5, that means the bottom number is a 5. Now I'll tell you, you'll get the same answer even if you put the 4 down there because of the symmetry. But the way that our formula is set up, we would put the 5 down there. Now we need 9 choose 5. My version of Pascal's triangle wasn't extended that far. Maybe you've already extended it to that row, but I haven't, so I'm going to use the calculator here. 9 math, scroll to probability, choice 3, choosing 5 objects. It's 126. X cubed to the 4th is x to the 12th. We needed that because we're looking for the term that contains x to the 12th. 2y to the 5th is 32y to the 5th. This is another calculation I can't do, so I need to take 126 times 32. That's 4,032. X to the 12th, y to the 5th, and now we have the term that contains an x to the 12th. I've got one of those for you to try here. I want you to find the term of the expansion of 7x minus 2y raised to the 12th power that contains y to the 20th. See if you can do that. Okay, so I know the terms of this expansion are going to be 12 choose something, 7x raised to some power, and negative 2y squared raised to some power. We want the term that contains y to the 20th, so we need a power on the last set of parentheses that will give us y to the 20th. Keeping in mind that we're raising a power to a power, we need to multiply by 10 here. So you're choosing 10 copies of the second term, that means this will be 12 choose 10. And if we've only chosen 10 terms so far, and there are 12 terms to choose total, that means we need 2 more here. So that will be 7x squared. And now we just simplify. So we'll get 12 choose 10 from the calculator. I believe this is 66. Math, probability, 3, choose 10, 66. When you square 7x, you're squaring the 7 and the x, so this is 49x squared. Here we're raising negative 2 to the 10th power. I happen to know that one. Negative 2 to the 10th is positive 1024. Y squared to the 10th is y to the 20th, and it better be, because remember, we're trying to get the term that contains a y to the 20th. Now I can't do that multiplication in my head. 66 times 49 times 1024 is 3,311,616. X squared, y to the 20th. You definitely don't want to do this one the long way, and in fact you don't even want to do this one by listing out all of the terms and hunting for the one that contains y to the 20th, because it'd be an enormous waste of time. Make sure that you can understand the logic here. I know that the skeleton of my term will look something like this, where I'm going to have some exponent on each of these factors. In order to get a y to the 20th, I needed 10 copies of y squared. If we're choosing 10 copies of the second term, then this is 12 choose 10 up front. But we've only selected 10 of the terms that we want. We need 12 total, so that means the other two must be 7x's. And now we just need to simplify. I strongly advise you to do some practice problems here. You want to do a few examples where you're finding the entire expansion of a binomial raised to a power. You also want to dig up some examples where you're finding specific terms. If you have questions about any of the examples in this video, or any examples that you're trying on your own, just reach out to me. We can talk during an office hour, or we can do this by email.